This lecture, we're going to talk about malaria and how we're going to model something like malaria. Okay, and before I move further, I'd like to address a few things about modeling and why is it important, and what's going on these days, and how the modeling helps on that criteria as well. So let's listen to some clips out there. I just grabbed some from the news out there. Okay.
Look at models, but we validate those models with the data that's coming in. And United States will look different than Europe, and Europe look different than Asia.
To thank and respect the modelers who have really worked on this, because there's a large number of them have worked very hard and done a lot of predictions. And what we did is we did predictions of predictions. We like to integrate data, and so that's
Okay, so you see in that little clip talking about how they predict things in this corona aspect, and so how is they going to handle that using the data, and then they model it. So this is the whole actual concept that what we doing, right? So we're looking at different models and how we're going to model things. You can see, you saw that she's appreciate all the people who doing the modeling and everything. So this is what exactly this class is about. So you're learning to do modeling in different different things out there, and different phenomenons, or something like the pandemic, which is like COVID-19. So whenever it is, well, each of those have different data that you gather together, and you predict things, right? You cannot wait until it happens. You have to see what's going to happen in the next few days and everything like that. So this is exactly what I'm asking you to do in your project as well. Now I think you have a little clear idea what I'm expecting from your reports at the end of the semester, right? So what you have to do is gather data and come up with a very feasible, realistic model of your topic, whatever you pick. So this is where everything clears out, I guess. All right. So okay. So and then I ask you to do the hypothesis of it, right? And then hypothesis means the analysis of the data, and then you come up with the conclusion, right? So yeah, this is another clip here that I have.
When, as I keep saying, when you take the data you have and you reinsert it into the model modifies. Data is real, model is hypothesis. Okay? So that's what you have to do, and that's what I think we're seeing.
Right, the data is real, but the model is hypothesis. Why is that? Because you're making some assumptions, right? So when you're doing a model, of course, you have to make some assumptions. So those assumptions are not exactly, we may ignored, some may be, you just think, okay, this is the situation. Why are you doing that? To reduce the complexity of the model, right? So because of that, even you have the real data, you can get only the approximation outcome, right? So that is why it's the hypothesis. It's not actually really going to happen in next few days. It can change by the data. So if you collect data today, and then you can model it and see what will happen according to the data that you collect today. But tomorrow it can be changed by the data you have for tomorrow, right? So that's something very important for to keep in mind, especially in the subject of modeling, right? Okay, so let's get back to malaria. So that's what we're going to model today, right? How we're going to analyze this. So that's what we're going to look at. Right. So first thing first, malaria is very dangerous. For mostly for the infants and the pregnant people, and also that's killing so many people than any other disease out there. Well, up to now, you can see each year there are like 600,000, more than 500,000 people die Well, that is like 1800 people per day. It comes in some days, I mean, in some seasons actually, but the weather making the important factor in here actually, especially in the warm countries, the malaria is common, but not any of the other countries. Like cold weather, the mosquitoes cannot stand. So in that case, it's not more common in Europe, but on the African countries, as well as South Asian countries. So you can see malaria as a bigger threat, right? So let's analyze this. And what is this? Okay, so before I go through the terms here, I'd like to introduce the scenario here, how malaria gets spread, and how does this whole thing works. Okay, right. It's very interesting. So if a person, let's say there's a person here and bitten by a mosquito which is having the malaria itself. So it's like, this is like the human infected the mosquito, and also mosquito can infect the human. So the carrier here, which is who's spreading this thing, is the mosquito, right? So there's a problem. I mean, there's a question of egg or the hen, that who came first kind of thing. But in general, what happens here is, if a mosquito bites a person who are already sick, so let's say this person is having carrying the sporocytes, which is the infected by another mosquito or whatever. So he's sick with malaria, and then there's a mosquito comes here and bite him, and later on, so he is now infected by the human, and then he flies away and bite another, right? So in this case, if you bite another, well, yes, in that case he gets sick by this mosquito. Okay, and that is the only way this will spread from human to human. So where is this human comes in? Where is the first malaria host comes in? Maybe he was cured by earlier by the malaria attack, and he might have some of them, whatever causing them, they infect the mosquito by his blood or something like that can be happen. But who get it first? That is a question. Interestingly, can ask anyone. Well, I don't have the answer for that. The way I read everything, it says, yeah, mosquito generally don't have, originally don't have, unless they get infected. So that is what we doing in this model as well. If a mosquito go and bite a person who has the malaria, that is when the mosquito get infected, and then the mosquito goes and bite another person, then this person get infected, right? And then if another mosquito comes in and let's say bites this person, right, and then this mosquito get infected, and then if he go and bite another person, he get infected. So this is like the mosquito thing. So the mosquito is the one who's carrying this disease from one person to the other. It's not like the COVID-19, which is the one person can cause that to another person. In this case, it's just the mosquito. There has to be existence of a mosquito who's infected by this disease in order to spread it through. So even if it is a very rare phenomenon that one mosquito has to bite a host, and then within certain days he has to bite another person in order to get sick. So well, even if it is that kind of a rare situation, still there are over 500,000 people, right, get sick get sick every year, right? So that is very interesting point. And 1800 people per day die when it comes to the malaria season. Well, this was under control for most of the countries nowadays, but still, when you take it as a whole, it's a fact. I mean, this many people still have affected by this kind of the threat. Okay, so this exists to up to date today. So that's why it is important we're looking at it, right? So so in this case we have two different kind of the groups. One is the mosquitoes, the other is human or whoever get affected by it, right? So let's go through some terms here, and then we'll analyze this further and see how we're going to model kind of something like this. Okay, right. So the vector is an animal that transmits the pathogen or something which is causing a disease. So something which is causes the disease we call pathogen, right? So that's what it means, right? And Anoplus is the mosquito that can host malaria causing plasmodium. So this is the carrier actually, right? So not all the mosquitoes have this ability, only for the one certain group called Anoplus, right? There are like 300 plus type of mosquitoes out there, different shapes, different sizes, but only ones who are causing this malaria is I think that group has 60 some species, right? Those are called Anoplus, right? Okay, so that is one thing that you have to know, right? And other than malaria, there's one more thing which is spreading by mosquitoes. We call that dengue or the dengue. So that is another one which is causing deaths. I think that is more common than malaria, because malaria was controlled after a certain time, right? Okay, and sporozoites, which is the infected agents that inject by a female mosquito into the human host. So this is what this is where the infectious agent going into the blood. How does that happen is, whenever a mosquito comes and inject you, right, the first thing mosquito want to do is melt your blood. So what does that means? Well, you know, when you're having a cut or something on your body, the blood start coming out and then it stops, right? How does that happen? Well, there's something it's clotting the blood when it comes out. Otherwise you will drain your whole blood out from a little cut, right? It's not going to happen like that. It's going to stop, right? So that has that clotting mechanism in your blood, right? So if it is clots like that, well, even the mosquito cannot get enough blood to their body because it's clots, right? So in that case, before any mosquito comes and sting you, right, the first thing it does is it's going to put its own saliva on your and the area that they're going to attack, right? So that is where these sporozoites will go into your body. Otherwise you won't get hurt either, right? And you don't get a red little big mark when the mosquito bites. That all happens because the mosquito is inject some the saliva to melt it the area that he's going to take the blood in, right? And that's where you aware you get to know that the mosquito bites you, right? And with that saliva, that's where the sporozoites going inside your body, right? So usually it is causing by the female mosquitoes, it says, right? And it can be a male or female who's the carrier of that, right? And whenever those sporozoites going inside your body, it will it will generate invasive cells. So that is actually a sexual phenomenon, which is multiplying one cell into multiple cells. So this is actually I post some videos, two of them, about the human host and the mosquito host, how that generate cells inside your body and then get affected or get sick by it. So please go through those two videos. It's very short ones, just to you can visualize what's actually going on when a mosquito bites. So that's why I just posted those things. Very helpful. Okay, so the merocytes are the cells which is multiplying inside your body, and it's produced by the sporozoites, offsprings of sporozoites, right? So anyway, so this is what actually causing you to get sick, right? So and then that's also generating something called gemetocytes, right? So the male and female merocytes, which return back to the mosquito host. This is what causing the mosquito sick actually, and then also the mosquito turn into the agent who's carrying this. Okay, so in this diagram you can see the sporocytes comes here. The asexual cell division means you don't need any reproduction mechanism on this case. It is not actually reproduction like male and female. It's just the nuclear division actually making more cells. So that's what it is. And the merocytes will go through the body just like the video that I just posted up there, and it will go into your red blood cells and then go through your body, right? So that's make you sick actually. And some mature into the males and females of gemetocytes, right? Gemetocytes, and then the male and female gemetocytes, fertilization happens, and oocysts, that is actually the division migration to the again this is where the mosquito get affected, right? So then sporocytes again on this cycle going on and on, right? So this is interaction between a human, and this happens throughout the interaction, and carrying to another person from one person. So this is the whole cycle of this disease and how it spreads and things like that, right? It is pretty different from what we're experiencing now with the COVID-19. So in that case, the COVID-19 is more contagious than malaria, right? The malaria has to have mosquitoes to carry it on, but not something like COVID, right? Okay, right. So before we move on and do this modeling, we have to do the assumptions, just like when you do any other model out there. You have to make it simplify first. Maybe we'll apply more parameters later, right? So the modeling is a big thing, right? Actually that gives you a lot of predictions and precautions that you are making depending on this, right? Especially up to date today about the COVID. There's all decisions made by the modeling, right? So whether if the model says, oh, you're going to die, you're going to get this many people infected, and the death rate will be like this, it will be rises like that, and so on. Those are actually predictions making by the model, right? So if you don't have the model, you cannot make any predictions. Maybe you can without any graphs and all that, just by looking at what happens in the different countries. But if there are no countries to compare, right, then it will be a problem. It's because each country to country it might be different, especially for malaria. You cannot compare with the other countries, because why? The malaria spreads very fast in the warm countries, like something closer to equator, right? African countries as well as South Asian countries, because they don't have the seasons. Mostly the whole 365 days is generally in the same range of temperature, not like getting cold or anything like that. So if it is getting colder and colder, yes, the mosquitoes cannot live in the cold weather. Their lifespan is very short anyway. So because of that, is controlled in certain areas, but not all the areas, right? Okay. So well, we consider only the humans and the mosquitoes in this case, right? So not the causing medium, we don't worry about it. So the plasmodium is not there. So we just apply only for these two groups, okay? And the population of human is a closed area, so no births, no immigration, or no deaths except from malaria. So this is how you simplify things, but it is not the reality, right? Even in COVID-19, maybe you have to first come up with some assumptions, and then you release a little bit more by the base on your factors. So but the first thing you do is you make serious assumptions, which is not actually realistic in this case, but you have no other choice to simplify your case, right? As soon as the vector bites a human, individual become host. This is not, in reality, it is not like that. You take like 2-3 days actually for human to get actually become a host. Like for example, if a one vector or the mosquito comes and bite you, and after 2 minutes if another one bites you, this is not going to happen, or the mosquito is not going to get affected by it, right? So in that case, yeah, we may have to consider that. But in this case, right, we'll say, well, that is not the case. Whenever somebody bites you, you become host, right? Right, no immunity, right? So whenever you get bite by one, you get sick. Either you have you had it before and you overcome it, too bad, doesn't matter, you get sick again. So that's what it means. And no incubation period, of course, is the same thing as soon as the vector bites, you get sick, right? But there is actually the incubation period, right? So that's what it shows in the videos prior to this one I just posted, right? Ignore the chance of relapse. What does that mean? Human hosts eventually become immune and the others die, okay, of course, and the still recover, become susceptible again. So that means what? Whenever you get sick and even you recover means you turn into a susceptible again. So what is susceptible? Well, we talked about that earlier. That means somebody who's vulnerable to have or become sick again, right? Okay, so and the death rates of infected and uninfected mosquitoes are identical. So what does this mean? Oh, it doesn't matter whether the mosquito is sick or not, they died in the same rate, right? Maybe it is not true or true, we don't know. Why? We have very little chance to figure out whether the mosquito is sick or not, right? So only way you can do it, catch them and just to get some samples of whatever they have and test them whether they are infected or not. So if you want to do that for millions of mosquitoes, it's not possible to do, right? So in that case, we just throw out an assumption like this, right? And all mosquitoes reproduce in the same rate, so that's another thing. At birth, mosquito is uninfected. Yes, so all the mosquitoes are clean when their birth, right? Only they get sick by when they bite a human or whatever it is, right? So you can, if you've seen mosquitoes, they lay eggs actually on the water, and it is like tadpoles kind of thing. You can see little tiny mosquitoes in the water first, and then they become something that they can fly right later on. So it's pretty interesting. It's just like tadpoles, which is the fish actually at the beginning, and turn into a frog, right? So that's the same kind of phenomenon on mosquitoes as well. They're coming from eggs, and they're like worms at the beginning, and then they turn into a mosquito, right? Okay, those are pretty nice to see when you look closer. If you have ever seen, I don't know whether this country has mostly, so you may are not aware of those things, so that's why I point that out, right? Infected mosquitoes, infected mosquito immediately become a host. Maybe it is true because they're taking enough blood into themselves, right, from the human who's infected, right? So this factor is taking short time, but some assumptions here, like as soon as a vector bites a human individual become host, he is not realistic, but we just put it up there in order to make our model more simplified. Okay, right, so let's move on. And the formulating a model, we have two types, right? So I think we already talked about SIR model, which is we have in SIR model we have what we have something called S, which is we call that susceptibles, right? So this is susceptibles, and then we have what the recovered, right, or the infected people. So we call this infected, right? Infected people, and then we had recovered, right? Recovered. On this case, this will be a little bit different from here. Susceptibles, yes, it will be the uninfected people, or in this case, or the recovered, right? So this is where the recovered comes. Oops, the recovered. Oh, what did I write here? Recovered, right? Yeah. So in this case, we are thinking of recovered as susceptible people, right? And then infected means, of course, the mosquito bite you and then you become. Instead of R here, we have something called immune. So that means what? So you don't have a recovered here. We have something called immune, right? Okay. So the immune means, well, they don't get sick when whatever happens. Even the mosquito bite you, you don't get sick. So these are the three groups we get. We get susceptibles, infected, and immune, right? But whenever you have a recovered from this disease, right, you consider them as can sick again or something like that. So that's the difference from what we have before and what we're going to put here, right? Okay. And then for mosquitoes, well, uninfected mosquitoes, that means again these are the kinds that we call as a susceptible, right? And susceptible type of mosquitoes, we call them uninfected mosquitoes. And then vector, which is actually infected ones, we call them a vector, right? So this is infected ones, infected, right? So you can see now this is the same terms that we use, I mean the same idea we use, but a little bit different here. We are using the uninfected and the human host, which is infected, and then immune, which is no effect from these things, right? But whenever you recovered, you become susceptible again. So that means you can have malaria more than one time. So that's what it means. Okay. And here, uninfected, again, we call susceptibles. Why? Because they are vulnerable. They can get sick, right? So that's what it is, right? And the infected we call the carriers, which is having they can spread this thing, right? So those are the things that we have to consider when it comes to the formulating these things, right? So, but we don't know whether the mosquito is sick or not. We don't have the data for that, right? So the only thing we can consider is infected and susceptibles. We don't know whether the mosquito ever going to get recover from what they get, right? Once they bite a human, and if they get sick just like human, and then you don't know whether this mosquito ever again going to heal from it or not, right? So that part is we ignored. So that's why we have two groups here, and for the human we have three groups. For the mosquitoes we have only two groups. Okay, right? So that's something. Keep asterisk on this one, on this slide. This is very important, and we just consider time as the t units, but maybe you can count as days, especially when you're gathering the data, right? Okay, so this is the diagram of this. So this is, you can see the human factor is on the top. So we have a human host, right? And then of course some people die, right? And some people are immune, right? But and there's another part of this, which is the recovered become susceptible, right? So yeah, there are some people never going to get sick, right? So that's going to go flow to immune. So these are immune people, whoever gets sick but immune, but they're never going to get again, right? So but in this case, well, let's also include the people who never get sick, but they can be the host, of course, right? When the mosquito comes and bite you, it might be in your blood, but it's not going to cause anything. So that's what the immune part is comes here, right? And the recovered, of course, sometimes there are three possibilities: either they die, they carried but there are no symptoms, or you recovered and then you become infected again, right? Okay, so this is the flow of that. So you have three rates here that you have to consider. The one is the death rate, the recovered rate, or nothing happens to the people, right? Right. So and then the mosquitoes, of course, we have uninfected mosquitoes. They will die naturally without any causing, or they get infected and become a vector, and then they die the other way, right? So those are two rates actually that you have to consider, right? Okay, so right, so this is how does it connected? Well, the human host can infect a mosquito, and the mosquito can infect human, right? The human can infect a mosquito, mosquito can infect a human. So that's what these two blue lines showing here. Okay, so when you model this, of course you need some equations, right? So what are the equations you need? Here are the equations that you need, right? Flow to immune is immune rate multiplied by host. That's one thing. And then the human host death, so that's include the malaria included death rate multiplied by human host. So that's the rate, right? And then the recovered, of course, the recovery rate multiplied by human host, right? So there's a rate. Rate means what? This will be some portion of this. It's always less than the number of humans. So this is always less than 1, right? So those are fractions actually. So that's why you multiply by the total number. So it will give you a fraction of this as immune, fraction of this as death, fraction of this as recovers. What is this? This means the human hosts, right? The total human people who have infected and or carrying the disease, right? I wouldn't say it's infected because of why? Because the immune rate is there as well. Okay, right? So they are carriers actually, and then the portions of those are the rates. Then you can get those three, right? And again, when you come to the mosquitoes, the birth rates, the births of mosquitoes will be what? The birth rate multiplied by mosquitoes. Mosquitoes is the total possible mosquitoes out there, right? So these are included, these mosquitoes are included uninfected and the infected, the vectors and uninfected mosquitoes. Only for the anophilous group, right? So the others you don't have to count in this case. It's only anophilous mosquitoes has this ability. The other mosquitoes don't get affected at all, right? Right. So an uninfected mosquito deaths will be the death rate of a mosquito multiplied by uninfected mosquitoes, and the vector deaths will be the death rate multiplied by vectors. So the death rate in this case is the same, right? You just remember that we made the assumption that the rate of deaths will be the same for the uninfected and the infected mosquitoes. So that's what this means, right? So it is the same value here in the both situations. And then there are some rates that we have to consider, right? So this is uninfected humans over time. That will be equal to, so this means the change of humans over change of time is the recovery rate multiplied by the human host, right, minus transmission constant multiplied by uninfected humans, right? So this is the equation for that, right? It's given there. And the transmission constant, how we calculate that, is a probability of you get bit, right? You get bit by mosquito, right? And it has to be a mosquito that is infected. So that is what we call transmission constant. So these probabilities are, well, the total bits that you get I mean total mosquitoes out there and how many bite you is the probability of bit, right? And the total mosquitoes out there, and then the probability of having a anophilus who is infected is the probability of vector means, right? Okay, so that means total mosquitoes over how many bits you multiply by the total mosquitoes and how many of them are actually sick when they bite you is the other probability. So those are probabilities. When you multiply those two, you get transmission constant. Okay, and then the uninfected humans over time, which is a recovery rate multiplied by the human host, right? So it's the same thing up here. It's here, right? Of course, multiplied by transmission constant. So this is the same equation in a different way of writing. Why? Because I'm introducing a transmission constant. Transmission constant is this. So here is a transmission constant. You have no clue what it is, but I'm just replacing this transmission constant by these two values. So what I'm saying here is this is a transmission constant, right? Oops, that's too big. Let me make a smaller one, right? So that is a transmission constant. So give me a second. Let me address that better. Okay, so this is transmission constant, right? And transmission constant is this one, which is nothing but the probabilities of the probability of you getting bit multiplied by probability of that bitten portion. I mean the factor is actually infected mosquito. So that is what the transmission constant is. So I'm going to apply these values to this, right? So instead of I'm using that, I'm writing the same thing here with that value here, right? So that's what it is. And the probability of vectors, yeah, that's what I just explained to you, which is the vectors over mosquitoes. So the number of mosquitoes and how many of them are actually got infected. So this is the infected number over the mosquitoes. How do I find that? Well, there's no certain way that you can say, okay, there are this many mosquitoes and these are the infected mosquitoes. So how are you going to manage this part right here is maybe you get a sample, right? So you can get a container of mosquitoes in there, right? So you get some total number and then mosquitoes, and see how many of them actually are sick. So you count that, right? So when you calculate it like that, you can decide, okay, so in this case, well, there are 20 mosquitoes here and only 5 of them are infected, so the probability will be this, right? And whatever the value you get here as a probability, so you may get actually several samples of this, and you analyze that and see whether it's going close to this value right here, which is 1/4, right? Yeah, 1/4, right? You can divide both by 5, right? So 1/4 equals what? 0.25, right? I guess, yeah, right? So this is the probability, right? So this probability, if you get another sample of data and then if you analyze this, if you get something like 0.23, you can get anything when it's closer, you get the average value. So that's how you calculate this thing, because we don't know how many mosquitoes who are anophilous in the world and how many infected. You can count that, right? So this is just a get some sample of them and see, and then you predict, okay, this is what it's going to be. Is that true? Maybe it is close enough, but it's never going to be accurate, right? So it's uncertainty. So that's why even in this COVID case, we saying the modeling is hypothesis, not actual real thing. The data is real most of the times in that case, but data also have these issues. So that's what I want to point out. Data is not always real in this case, right? Okay, so that is also you have to take into fact, right? You can miss data, of course. You don't know, for the COVID case, you don't know whether you encountered all the people who are sick. Maybe some people are not noticed at all, but they were sick, right? So in the things like that can happen. So not data even accurate, but you had to assume it is. Okay, so and right, so let's move on to the next part, which is we are calculating here, which is uninfected. So we went through this, right? So the vectors of the mosquito. So I can apply this one also into right here, right? So now I have the probability of the bit multiplied by vectors, which is the vectors, and the uninfected humans divided by mosquitoes. How does this part comes in? Well, I apply this part using this to this, right? So when you do that, you can write it in this way, right? So yeah, this is much more easy way to use this, right? And probability of how much you get bit by mosquitoes, well, you have to count that. No, I don't know. This is also a sample that potential of you get bitten by mosquito is high in the areas if you live with the mosquitoes, right? And other areas, if there are no much mosquitoes, you don't have to worry about it. So even this one is not the real data, it is just an assumption based on sampling actually, right? So those are called sampling. So you get some samples, right? And then okay, so the vector change in vector amount is the flow to the host, right? So what is flow to the host means? Well, the probability of probability bite, the human get bitten multiplied by probability of a host and multiplied by uninfected mosquito. So all three calculations here we apply into this part right here, right? So the probability of host means the human host divided by humans, right? So that is also the humans you consider as uninfected human, and the human host, and then the immune means no infection at all, right? So all three means the total humans, and the probability of host is nothing but so this part right here is nothing but human host divided by that. Okay, so that is what this is just uninfected here, the mosquitoes, right? So it is 1 minus infected of mosquitoes, you can get this one, uninfected mosquitoes, right? If you get a probability, otherwise it's just a value, right? So let's move on to the next one, which is when you say the submodel of human submodel. So this is a human submodel. We looking into more details here, right? So recovery rate, and then I have now the malaria included death rate, right? And then I have immune rate and all that. So you see that when you consider those equations here, right, and we apply some of these probabilities, okay, so we break these values now into more details here, right? So you can see now the probability of vector, probability of bit, right, probability of host, and all that we gonna apply into each of these sections, so you can make it more detailed. So what we had before on this model right here, this is a submodel of the top part right here. This is a submodel of human, right, infected humans, and on this one we just analyze these things, right, these things and these things depending on other values, right? So there are more values now come into play with this. So those are values that we consider that we're going to use actual calculations. So this is what it is, right? So when you putting these things into play, and the same for the mosquito part, right? So now the uninfected mosquito deaths, you can say mosquito death rate you are applying here, and also mosquito death rate, the same value we can apply it here, or either you can have it in a two different little values like this, or you can have the same arrow to this one as well, right, and then get rid of this. So that is a shortcut you can do in the diagram if you want to do that, right? Okay, and then also you have mosquitoes, of course, the same amount, the probability of a vector and the probability of a birth rate, so you have to consider this one, right? So the why is it affecting here? Well, that is the same thing that we said, the current probability, the change of population is equal to the rate of births, right, births multiplied by, right, birth rate, actually birth rate multiplied by the previous population, right, the previous population. So in this case the previous population is the mosquitoes right here, right? So this is actually we learn in the population growth, it's applied for the bacteria, it's applied for everything. So yes, so that is what it is. And then the probability of a vector out of that, well, you need the total mosquitoes over that, and then you say this many affected. And also the probability of human bite, this is actually the human total human divided by infected human, so this is the probability of that. And bite by a mosquito, of course you have to multiply by that too, the probability. So you get those values, and then you can have this detailed submodel for the mosquitoes as well, right? So now you can see how complicated it's getting, right? So you have to draw this many things, that's why the software is helpful for you, right? I don't know what other softwares is using by the COVID-19 modeling, but still they might have their own kind of modeling with the high-end calculations. or whatever it is. Well, that's what you do, right? So in this class what you're learning is analyzing different models. I hope you have idea now what is actually learning in the class, right? All right, so now when it comes to the results, so you can see it's pretty interesting how it's laid out, the simulation, right? So this is a T is the time. I think it's out of days. I can't remember, I cannot recall what it is actually. Maybe, yeah, it should be days actually. And right, so this is a scale for everything. The total number, it can be a vector, it can be human, uninfected humans, and immune people, and then the host, right? And suppose like that. So when you analyze this, it doesn't make much sense when you're looking at these things, right? But anyway, so this is what you get out from these simulations by applying these parameters. Okay, right. I think it's better you have a table on this and see what are each of these values means and how that affects. So you can see the uninfected humans starting with 300 and it's going down. So all the people are infected in that case, right? So then there are some people who are immune, is going up like this, right? And then some of them will add into again uninfected, and then it's coming back. So that's why this line is higher than the hosts, right? Okay, right. And then uninfected mosquitoes, right, getting infected. So uninfected at the beginning, and they're dropping down, and then well, they might die, and again the birth comes in. So that's how it is, right? So right, so let's move on. So these are the exercises on this book. There's few of them I'd like you to know. So these are things I'm expecting you to know mostly. The terms at the beginning, I'd like you to remember those things as well, and the submodels, how you divide it to submodels. So this is one of the two submodels is given you, and then each category of this. So keep asterisk on this one. I'd like you to understand this in this model. Give the major submodels of the material, malaria models, right? So it is a human and mosquitoes. So those are the two models that we're going to consider in this case, right? And list major categories of organisms for a model, right? So the uninfected humans, human host, and the immune in this case, right? And then for the mosquito group, we have uninfected mosquitoes and the mosquito vectors. So those are two kinds for that, right? And yeah, so these are the things which is coming from the diagram. So if you know how to read the diagram, you can come up with these things right here, right? So it says destination flow from uninfected human. So when you go back to this one right here, so this is an uninfected human. So what is the destination? So you have infected human, so and then it goes and end, it's a human host. So this is where the arrow ends. So that is the destination, right? So the human host, the destinations, there are three of them, right? For the human host, there's one which is called uninfected human, and the other destination is the death, and the other is immune. So there are three for the human host, if you say. So like that, you can go through each of them, right? And then figure out. For example, mosquito hosts, mosquito birds. So the destination is uninfected mosquito, right? From there are two of them actually. Uninfected mosquito is the one destination. The other is vector or the infected mosquitoes, like that. So that is how you figure out the destination flow, and that is what it's asking here. How do you really going to figure out where it is? Well, that is nothing but where it ends, right? The destination flow for the human host, you can see uninfected humans, immune, and then diseased, right? And so on. I think you can figure these things by yourself by looking at the diagram, right? It's easy where the not, I mean the end of your arrow is the arrowhead, that will tell you where it is. And given that the immune over time, so that's the immunity rate multiplied by human host. So if the immunity rate is 0.2 and there are like 500 human hosts, and the immunity is and the immune is 400. So what does that means? Estimate the number of immune people at day 6.1. So that means what? So that's a day here, right? So we have to consider the immune of this day, right, is equal to what? Immune of the previous day, right, plus the immune rate multiplied by the human host of the previous human host multiplied by the delta t, right? So how do I calculate this? Well, what are the things I know here? So the immune of the previous day is what? The immune is what? 400. So this is 400, the previous value, right? And how do I know this? Well, immune rate is, this is actually the current value equals old value plus the change, right? So this is the change, actually this is the change, right? So this is the delta, whatever the p we can call it, right? This is earlier value plus the change is equal to new value, right? So this is actually the new is equal to, right, old plus the change, right? So this is what it is, right? So the change is always a rate. So that's what's given by this one right here. So this one says immunity rate, right? So the immunity rate is 0.2. So this is 0.2, right? You multiply that by what? The host, right? So the host is human host, previous host is 500, right? So this is 500. Multiply by the time interval. So this is 6.1, right? What does that mean? Well, the delta t is 0.1. So the delta t is 0.1 because 6.1. So that means the one interval after. So when you apply this, well, this is what you get right here, right? And this is the answer. So I hope you understand this. What is this means is new is equal to old plus the change. So now you know what is dt by d immune by dt, or the d whatever it is, means always a change, right? So if you have something seen with the d and the dt, that is the change, nothing but the change, right? So this is called finite difference equation, as you recall it before lectures, right? Now I think it's much more clear when you're looking at these things, right? Right. So if you study well, yeah, you know now. Okay, so now, right, so let's look at this one right here. And then transmission constant. We're talking about transmission constant. I talked about this a little earlier as well. And so this is the rate, which means the change, right? So the uninfected humans, how many is going to change? Is equal to recovery rate of human host, right? This part is recovery rate that you should know some value. Let's say it's given to you, right? Multiply by how many people were there. Minus and transmission constant. So this is something that we talk about with the probabilities, right? So here again it's explaining, and uninfected humans, of course. So the probability of that human is bitten by mosquito is one probability, and then the other one is probability that mosquito is a vector is another one. So if you multiply these two together, you get the transmitted constant, which is, here is an example of it. So this is 60 is mosquito bitten by person, and that mosquito is vector. In that case, this is what you get as a transmission constant, right? So if I want to write this, the change, or if somebody asks, what is the number or the total uninfected human after t plus 0.1 time, right? So this is equal to what? This is equal to old value, which is uninfected human, underscore human, let's say, of the previous time, which is the time t, right, plus the change. What is the change? Change is this one right here, right? So that is a recovery rate. In my example, recovery rate, right, recovery rate multiplied by the human host at t time, right, minus, okay, transmission constant. This is where this value comes in, multiplied by uninfected humans, right, uninfected humans, the same thing previously. Right. So this is actually the people who are the time little bit before this value, right? And you multiply this by what? You multiply this by 0.1. Right. So this is what actual value is going to be, the current uninfected humans. Okay, so the current uninfected humans is equal to old uninfected humans plus this value right here. So that's what I don't have the notes for that, but this is what it means. So that is the same thing I just want to point out in my previous one, which is this slide right here is talking about that. So keep in mind, this is the change. This is what I want to point out. Okay, right. So this is actually the possible questions I would ask you, and well, I can ask more, like any rate like this. So beware on the quizzes. I would ask you something is not here, which is not in these notes. That is, but you should understand what is this slide means. So keep asterisk on this. Make sure you understand this. What is this rate thing means, right? Right. So what is this means, and then how you apply that to your equation, right? So this is the exact question, kind of a question I would ask you. So make sure you understand these things, especially your exams is going to be open book, and then your quiz is going to be open book. So only way that I cannot actually test you or inspect you when you're doing the exam, because there are so many people, too many people. I think the max capacity also 40 for the Zoom, and not everybody has cameras. So in that case, I cannot monitor you. So that because of that, I give you open book quizzes and open book exams. So that means I'm not going to ask as is like I used to do in the quizzes in the class, right? But now I'm expecting you to understand things. So when I ask you a question, it is not going to be in the book like it used to be. So you need to understand the concept behind it. Especially in this case, you can see now what is this d immune by dt. So you have to understand what this is. So this is exactly what underlined here, right? And so if you have understanding, of course, you can apply the same concept to these things on the later on, right? So in these values. So yeah, so I'm expecting you to understand things more than you just memorize the things in the book, right? Okay, so yeah, we will talk about a little bit more theory based math on the next lecture, which is errors, how we're going to calculate the errors, and what is the magnitude that causing to modeling. Okay, so we're going to look at those in the next one. Right, so I'll see you in another next lecture.